find solutions of this equation. Okay, so the equation is x to the n plus y to the n equals 2 times z squared, okay, where n is bigger than or equal to 7. Okay, what we are going to do is that we are rather going to show that x to the p plus y to the p, right? I mean, we are going to look at the equation x to the p plus y to the p equals 2z squared for n a prime number, okay? So, z squared and p is bigger than or equal to 7. Okay, so so suppose I say that I'm going to assume that this has non-trivial solutions, which means they are pairwise coprime and x, y, z, the product is not equal to 0. Okay, so suppose x, y, z equals a, b, c is a pairwise coprime solution with okay, so as this is even, this side is even, they necessarily have to be odd. Okay, so AB is odd, right? So, so here, AB, individually they are odd, AB is necessarily odd. Okay, and the associated Frey curve is so the Frey curve is given by y squared equals x times x squared plus 4c x plus 2 times e to the power of b. Okay, and we compute the discriminant. This is 2 to the 6 times square power of b, and this is okay. So this you can compute using these coefficients, and then the conductor of the elliptic curve n is 2 to the 8 times product b divides AB. So this is the radical of AB. Okay, so now we would have been very happy, like if we can show that, well, so take this elliptic curve and then apply Ribet's level lower condition. But there is one condition, is that I need the modularity of E, right? And modularity of E, as well as proved, needs the condition that my n be semi-stable, right? So which means that this has to be square-free. I mean, if that is square-free, then it's semi-stable. But as you can see that here is a power of 2 occurring here, right? So I have to resort to the general Brouwer-Conrad Diamond-Taylor theorem, okay, to get modularity. Okay, and also note that maybe okay. So So xy equals 0, 0 is Q rational point of order 2. Okay. So let x equal to 0, y equal to 0. This give us. So along with this point and the point at infinity, we have. We know that there are at least two torsion points on the rational point on the elliptic curve. Okay, so now let's make one more observation. Okay, so lemma, it's about the nature of this curve. Okay, so suppose maybe I should. Okay, so suppose, so recall that I have p bigger than or equal to 7. Okay, and p divides AB. Okay, so p is prime here. P prime. This is something very basic. Then the J invariant of E. Okay, so this is not integral. Okay, and the order is not integral, means it's not an integer, and the order of P dividing JE, so this is less than 0. So in particular, okay, so these are particular. It's not difficult to see this. Plus minus 1, then E does not have CM. So this is, okay, this is going to, okay, so the proof is easy. Okay, I will tell you what the proof is. It needs Silverman this elliptic curves. Okay, so the first thing you have to observe is that if I have a prime P that divides AB, which is bigger than or equal to 7, right? So then it divides n just once, right? So which means that my P will be a prime of multiplicative reduction. Okay, so note that E has, it could be split, non-split, that needs further study, but multiplicative reduction at P. Okay, so remember that this P is odd, so that's the reason. So this implies that, so once you have an elliptic curve which has got multiplicative reduction, it always remains, it's never going to attain good reduction even if you do any base change, right? So, so you say that, right? So E does not have potential good reduction at P. So any P you can take here that divides AB just once. So what does this mean? This implies that if you go to Silverman and then you open up chapter number 7 and then 5.5, section 5.5, you see that this means that the J invariant of the elliptic curve does not belong to ZP, right? So this is from Silverman, not the advanced Silverman. Okay, Silverman. Right? So when I say E has multiplicative reduction at P, I'm looking at the elliptic curve, okay, defined over the local field QP, okay, and it's a result that, so Silverman does it more general, that it doesn't belong to the ring of integers of QP, which is ZP here. So here I'm taking QP and then ZP. So what does this mean? It means that, but JE, I can calculate using the coefficients here, is going to be a rational number, right? And it's not inside ZP, which means that, JE, okay, so, is not integral, right? And the order of P, the order of P dividing ZA is less than 0. Okay, so in particular, if AB is equal to 1, if AB is not equal to 1, then you will have an odd prime, so what do I say? Yeah, you will have an odd prime dividing AB, right? Then this is never going to be integral, and yeah, so somehow, so now this is not equal to 1, okay? So if AB is not equal to plus minus 1, then you know that you will have an odd prime P dividing this, right? So then JE, this is not inside Z, right? So which means that my E cannot be an elliptic curve with complex multiplication, right? So this implies that E does not have CM. Okay, so if you have an elliptic curve with complex multiplication, right, and the J invariant is always an algebraic integer, you have to look at the automorphisms of C defined over Q, right? Then you have to say that, calculate that J of E sigma is sigma of JE, and then it will prove to you that J invariant is an algebraic integer. It doesn't happen. So now, so associated to this elliptic curve, okay, so attached to E, I have a Galois representation. So attached to E, okay, so I have a Galois representation rho, okay, E, let me write here a P. So the Galois group of Q bar over Q, okay, to GL2 of GL2 of ZP, right? But then I can take the reduction modulo P, and then I can get here FP here. Okay, right? So this is so the existence of this is, yeah. So this is, you have to look at the Tate module, and then so now it's the small proposition. So proposition. Okay, so later on, so what is the significance? So remember this lemma. So what is the significance of this? The significance of this is that I'm going to have a contradiction. I'm going to get a contradiction at this. Okay, so I'm going to show that the modular form that is associated to E will have complex multiplication. Okay, that elliptic curve. Okay, and then that will give me a contradiction, because then I will also show that AB has to be equal to plus minus 1. So if AB equals plus minus 1 and P is bigger than or equal to 7, then so rho E, so P is absolutely irreducible. Right, so the proof is, okay, so this relies, so it's enough to prove that, so as Ganesh was saying last time, that you just need, for a statement like this, if you know that if I can prove that rho EP is irreducible, then it automatically follows that this is absolutely irreducible. Yeah, because this has got, this is what you call an odd representation, means, right? The complex conjugation is an element here, and determinant of, yeah, I can look at rho E P and then look at complex conjugation here, right? So this is equal to minus 1. So when you have such a thing, then irreducibility implies absolute irreducibility. Okay? So it's enough for us to show that this is irreducible. Okay, So enough to prove that my rho E P is reducible. Okay, so anyway, so let's leave it there. Okay, so my idea was that after this I will have to apply a theorem of Mazur and Kubert, saying that P is a prime, and you know, we are not allowed to have points of order 2p. Okay, that's not possible. So that follows from a result of Mazur and Kubert. Okay, so that was my idea. But anyway, so we'll examine to this this again. So now let's compute our NP. Okay, so here NP. Okay, so this I put an E here. Okay, because this refers to this curve. So this is equal to 6 times okay, and this is the conductor. So maybe I see. Okay, then so okay, so suppose this is prime, then my rho E P, this arises from a new form. Okay, so this is of weight 2, level this one, and NPE, and trivial character, and trivial character. Okay, so here, so this is, so I should not say that this is a lemma, so this is actually a theorem. Okay, this is this follows from the proof of Broel, Conrad, Diamond, and Teller, and I guess it even follows from a result due to Broel, Conrad, and Diamond, which is prior to this BCDT theorem, which says that if 27 does not divide this level, then elliptic curves defined over Q are modular. Okay, so this is stated B. Okay, but if you observe that this is this rho E P is odd, right? So you can directly use this Curry-Winterberger also. Okay, and the trivial Niven type, trivial character is a theorem due to Ribet. Okay, so so I think the name of the article is what? Refined Conjectures of Sayre, right? So where he proves that such a condition where this trivial character, this you have trivial character. Okay, so you have to construct that representation. Okay, and so trivial Niven type, trivial character, this is due to Ribet. Okay, the name of the article is Refined Conjectures of. So just look it up, find. All right. So so now, so I have to find, right? I have to find now find modular forms of level 256. Okay. So lemma there are 6 new forms of with 2 level 256 and okay, so this is discounting dimensions. Okay, so let's do that. So proof. Okay, so I have this representation rho EP. So attached to this representation, there is something called a Serre conductor. Okay, so so far we have been talking about conductors of elliptic curves, but attached to this representation also there is a conductor which tells you about the ramification behavior of the Galois representation. Okay, so you can compute that. Okay, and the Serre conductor of rho En, this also turns out to be this 2 to 256, 2 to the power 8, right? Now, so let here S nu, so this is some general notation. So this is space of wet 2. Okay, so this is S gamma naught 2 to the R. Okay, so this is the space of with 2 newforms. This is a subspace of the space of cusp forms. And on the space of cusp forms, there is something called the Peterson inner product. So the orthogonal complement of this space, of this subspace inside the full space of cusp forms, okay? The orthogonal complement, that's called the space of all forms, okay? And S to all gamma naught to the R. So this is the space of all forms of wet 2. All forms of wet 2. Okay? And let's write dr for the dimension of this space, gamma naught, right? And dr new, let's put dr old okay. Then there is a formula okay. So what is the formula? Then dr old equals summation j equals 1 to r minus 1 r plus j minus 1 dj mu. Okay, so this is done in Miyake, okay, Miyake's book. This is, let's say, by theory of new forms. Okay, then so let me just write down the reference here. So it's Miyake's book on modular forms. So theorem. Okay, it's very nicely explained here in this. dj nu equals 0 if 1 is less than or equal to j is less than or equal to 4, and Okay, 2 to the power 6. This is 4 to the power 6. 1 and okay. So how many are there? So 6 new forms of weight 2 level 256. Okay, 6 new forms. This one. Okay, so the idea is to write down these new forms explicitly. Okay. For that, let me just explain to you briefly how to write down new forms. Okay, so sometimes you have to just take a pencil and pen and then write down the new forms. But before that, let me explain something. Okay, maybe I have to explain this. So I'm going to construct these modular forms, these new forms, by using Hecke characters over imaginary quadratic fields. Okay, so so we're going to construct these new forms. Okay, right? So suppose I have K to be an imaginary quadratic field. Okay, I'm going to give you some basic definitions. Then let's embed this inside C. Okay, so I have an embedding inside C. And I denote, so OK, so this is the ring of integers of K, and AK with ideals of K. So what is this? So this consists of this is a subset of the infinite product of all the completions of K over all possible primes. So it is alpha P, okay, where alpha P belongs to Kp for all primes P of K, and alpha P belongs to O Kp except for finitely many P's. Okay? So finally, right? So you take the product O Kp, right? And you take something like this. So if the xp's are inside. So if the xp's are inside OKP for infinitely, except for finitely many xp's, then you say that it's an element of this. So this is a ring actually. K is a very important ring. Now I'm going to define what a Hecke character is, and attached to that Hecke character, I'm going to attach a modular cusp form, okay? And then once we do that, we show that this 6 new forms are nothing but those which arise out of Heike characters. Okay, so you might be wondering, we wanted to solve an equation, but the equation is not coming out anywhere. It's because we want to find this space of new forms. Okay, so Heike character, maybe I should just define, right? I mean, okay, so now a Heike character is going to be a character of this, okay, of the units of this group. So let chi from AK star to C star be homomorphism of groups such that chi restricted to K star, okay? So this is identity. So this K, it sits inside each one of them, right? K sits inside each one of them. Chi restricted to C star. So if you take P to be the infinite prime, then this is nothing but C, right? This is 1, and the chi on an open subgroup, okay, of this pi OK P product star. So this is also equal to 1. An open subgroup of OKP looks like 1 plus P, this prime ideal, okay? So such a chi is called a Heike character. Don't forget this. Such a chi is called a Heike character. Okay. Now, so now I have this character, and so for this character we also have a conductor, and the conductor of chi is the integral ideal, okay? Integral ideal, which is defined by, these are all usual things, okay? So n is Gothic n chi. This is defined to be the product of all the primes, e to the power rp. Okay, so where rp is equal to the maximum r, where chi of 1 plus e to the r, say minus 1, maybe this is not equal to 1, otherwise we have to add a 1 here, so I want to do that. It's not equal to 1, and 0 otherwise. You can see this. So this is these things are usual things. Okay, so this is if chi p, if chi of what do you call OKP not equal to 1. Okay, so this is what a Heike character is, algebraic Heike character. Okay. Yeah, so maybe I should use the word algebraic Heike character. Okay. And here's another character which is called Heike character. This is algebraic Heike character. Okay, so there is a distinction between them. And that will be defined as a character of OK. Okay, so let me do that. Not OK, but the, what you call, the fractional ideals of K. Okay. Okay, so attached to chi. Okay, you can attach. We have Hecke character. Okay, so how do you get this? So the Hecke character is defined on the fractional ideals of K. Okay, so suppose I have A to be a fractional ideal of K. All right, and attached to this, I have I'm going to look at an element of these ideals of AK. Okay, so I'm going to consider an infinite sequence AA like this. Okay, so AA is A, B. This belongs to AK. So first, let's have this element given by A. So this is equal to 1 at infinite primes. The Archimedean primes, it is 1, and it is pi to the power of r, where r is equal to the order of, right, and then this pi is the uniformizer of this p. Okay, so this is called, so attached to A, I have attached an element in the adelic, in the adels, in the ring of adels. Then, so the remark is that this element, as you see here, this is not well defined. Okay, so that's why it's not I have not given a map as such. It's not defined, not well defined. Okay, but the value of the algebraic Hecke character on each one of them is well defined. Okay, so remark AA is not well defined. Okay, but if A is co-prime to n chi, okay, so n Gothic n chi, then it is well defined. Okay, then this makes sense. Then chi of this is well defined. Okay, before reading class field theory, you would have seen all these things. So this value of chi on AA, we again denote it by chi of A. Okay, so this value of chi of AA, okay, A, denoted by chi of A. Okay, and now, so we are almost done defining Hecke characters. Okay, so now, so now this is the character, what I'm going to write, character A, the fractional ideal of K, okay? So that's to chi of A, this one, this value. Chi of A means chi of AA, okay? This times the norm of A, power of minus half, minus 1.5. Okay, so this is a character on the group of fractional ideals of okay. Okay, and we can also say modulo of modulus. Okay? If you remember, we can drop this, but modulus n chi. Okay, so this power minus half is not so serious. I can take something like some other thing also here. Okay? Yeah, co-prime to n chi, okay? Maybe I can just write like this. Now, so all these things you can find much more in much details in the book by Miyake, okay? On the modular forms. So, yeah. So I'm going to write down the theorem. Okay, so Miyake theorem 4.8.2 here. Okay, so remember that my K is an imaginary quadratic field, okay? So this is an imaginary quadratic field, right? And dk be the discriminant of K, and the chi K is this character. Chi K is this character. It's like your Lisonder symbol. Okay, and this is a Dirichlet character. Of attached to K. And suppose I have K, chi, okay, is an algebraic Hecke character. Okay, of K, okay, say conductor n chi and conductor n chi, right? Then I'm going to write down a power series expansion here, f chi, okay, this is summation n equals 1 to infinity. So A and chi, I need this condition even to talk about this character. And the norm of A equals n, right? And chi of A here. And then here e to the power 2 pi I and z. Okay, so e to the power 2 pi I z is e to the power 2 pi I z. We have always used the notation q for this. So this is q to the power of n. Okay, and then this power series expansion. Okay, this is a cusp form. Okay, so that's the conclusion of the statement. Then this is this is a, okay, so here A runs over all ideals, okay, which are co-prime to this n chi integral ideals. Okay, A is, this is a new form of wet 2, okay, and the level is given by level n chi, so this is dk times the norm of n chi. This is pretty simple, pretty neat, okay, and of course it comes attached with Nibben type. Nibben type is character which is related to chi k, but to this one, but I'm not writing it down. Okay, so I have it. Okay, this has some Nibben type. It's not trivial. Okay, so now I have this cusp form. Okay, and then these ones will be the candidates for my 6 new forms. Okay. So this is one general way of writing down, one nice way of writing down cusp forms. Okay, so just let me add this. So F, a cusp form, is said to have Cm, okay, Cm means complex multiplication, okay, by K if F equals F chi for some algebraic character. All right, so what else do I need? Yeah, so now, how much time do I have? 6 minutes left. Okay, so I have to really hurry up. Okay, so now with this recipe, okay, what I do is that, so now, so let k equals q square root of -1 or q square root of -2, one of them. Okay. Why don't I take other imaginary quadratic fields? It's because my level suggests that it will be fruitful to look at this and this. Elliptic curves with complex multiplication defined over this one, okay, have conductor 32. Okay, so gives me this power of 2. Yeah, so so suppose I have a chi from O, W star, so W is a prime in K here, to C star, okay, so this is a character such that chi restricted to O star is equal to identity. Yeah, so O can be embedded inside OW, right? And O star, I'm looking at O star as elements of O and then inside OW. Okay, so this is completion with respect to a prime. And the chi restricted to 1 plus omega to the r, so this is equal to 1 for some r. What happens? So it takes some time to. So now I'm going to extend this character chi to the whole of my ideals, to my ring AK. So now extend chi to AK. Okay, so AK times, so remember that this has like, this looks like product of, no, maybe I write here OV, here, so, okay, by putting, okay, chi, okay, to be trivial on C, so chi here, this is trivial, 1, and chi, this is, okay, or V star, this is also equal to V, if V does not belong to W, and I have to do it on here also, chi, so this is identity. All right, so now I have extended my chi to my whole of AK, then I get an algebraic Hecke character. Okay, so, and I'm going to denote that extended Hecke character again, by chi, okay? So, denote this character again by chi, then I can write down all those chi's, okay? So just for this, to simplify notations, let's use this to, so this is 6, if k equals q square root of minus 1, and 5, if k equals square root of negative 2 here. So, yeah, so, well, I don't have a time to write down all the characters, but the thing is that we can write down, okay, I have it written, but I can write down 6 characters of conductor R of K. Okay, and the associated attached F chi I. Okay, so this is a new form of weight 2 and level 256 and trivial and even type. Okay, and the 6 ones are all the ones that you have written, because by dimension considerations, you know that there are only 6 of them. Okay, so now let me quickly run through, finish the proof of the non-existence of the solutions. So the idea is to show that, okay, so the aim is to show that AB is equal to plus minus 1. Just suppose AB equals, this is not equal to plus minus 1, then this implies that this arises from a new form of, right, of weight. So E arises from new form of weight 2 level 256. Just give me 2 minutes and then I'll finish this trivial character. Okay, and now what you have to do is that you have to look at these two fields, k equals q square root of minus 1 and the q square root of minus 2. Okay, and then you attach to f chi, to each of these f chi i's, right? You will have, these are new forms, so it will have associated Galois representations. Okay, so it's still a long way to go, but so all those, so f chi I have, and then attached to, I will have rho f chi I, right? And what you do is that, still not over, so you have to determine, okay, the image of a delicate study of the images of this rho f chi I inside GL2 of Fp. Okay, and then you'll remove. Okay, and then from there by so the images are all well known. It's either GL2 or it contains, if it contains SL2, then it will be the whole of GL2. Otherwise, it's a normalizer of a split Cartan and so on, or otherwise it's reducible. So the images of this mod P are well known. So using that, you can knock off some cases, and then finally you will conclude that you are left with only two cases. Okay, so P is equal to 7 or 13. The rest will be taken care of by a study of this rho f chi I, individual study, right? You have to restrict rho f chi I to every decomposition subgroup, and then you look at the ramification behavior. Okay, plus ramification behavior. Okay, then this, P equals, so out of this again, okay, if P is equal to 7, then your A times B is forced to be a power of 2. Okay, so which again is not possible because you have AB to be to be odd, A times B to be odd. So you are left only with P is equal to 13. To eliminate the case P is equal to 13, so to eliminate P equals 13 case, what you do is that you have to look at all possible elliptic curves of conductor 26, and then you have two elliptic curves. So one is called 26b, and the other one is called 208d. They all have rank 0, but somehow you will see that this case P is equal to 13. The curves that you have found has a point of infinite order. Okay, so that's the contradiction. So somehow I'm sorry that I couldn't do justice, but I just wanted to show that we have to write down all possible new forms. Sometimes we have to use computational techniques to do it. Okay, Any questions? Yeah. 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 Yeah, but my this is norm is times is norm to the power minus half. Yeah. Where? Oh, this one. This one. This one. Yeah. Yeah. Yeah, so I know. AB has to be plus minus 1. Yeah. No, but if AB is plus minus 1, then A is forced to be either plus minus 1, so A to the P plus Z to the B to the P will be 0, and then Z will be forced to be 0, and then ABC is 0, so that's not possible. 1 would be a solution, yeah. Yeah. Okay, so we can anyway discuss after the talk here.